Doing the advanced trig stuff, we've just been going back over it, and hopefully, as we were just mentioning this morning, as you're going through these ideas, you're like, oh good, I really get this now, I'm far more familiar with it. You're like, okay, it's clicking, alright? Well, at least I hope. So we've covered derivatives of the basic functions, the reciprocal functions, the inverse functions. We've covered general solution and auxiliary angle. So T results, okay? Now, by the way, before I get to showing you this, I'm not giving you any more exercises today because T results is just an alternative way to look at the questions you've already got. So I think actually T results get mentioned or they're a viable option for a lot of the HSC questions I've already given you. So, at least in this lesson, next lesson will be another question. I'm not going to give you another sheet, alright? I'm just going to show you this and then you can use it for all the questions you've already got. So, where do these things come from? Do you remember? What does it start from? What's the basic idea that underpins all of these? Yeah, so we're taking, it's sort of like a half angle result. So we let tan of anything, where theta is usually the convention, but you can use x if you want. Let tan theta on 2 equal to t. Okay? So then our mission is, how do we get the regular functions in terms of this, and then you can use it to do all kinds of algebraic fun. Okay? So, we go from tan theta on 2 to tan theta, okay? So, you're going to use the double angle result for this. So, all of this will be, in terms of t, okay? So, on the top you'd have tan theta on 2 plus tan theta on 2, which is t plus t. So, that's what we've got, 2t, right, on the numerator. And the double angle result for tan gives you what on the denominator? 1 minus t squared. And the way to remember it is the top is plus, the bottom is minus, or whatever, flipped around, okay? Alright, so from there, you draw your triangle, right? Right angle triangle, you put theta in a corner, okay? And because it's tan, it's opposite over adjacent, so it gives you this ratio. Okay? And from there, you can say, well, by Pythagoras, the hypotenuse should be equal to 1 plus t squared. Okay? You can check out the algebra in Pythagoras if you're not sure about that. So now that I've got my triangle, I can get all of my ratios, not just tan, but sine will be opposite, again, but on hypotenuse, and cos is adjacent on hypotenuse. Okay, so great. Now, you remember we use these three results, you can use them for all kinds of things. I think when we were covering it last year, we focused on using it for identities. Because when you're trying to prove this is equal to that, you start from one side, you've got to go to the other, and sometimes you've got to see weird tricks, and you've got to add something and subtract it at the same time, or multiply and divide, and it can be very confusing. But here, when you've got the algebra, bless you, it all just sort of falls out, right? And you just have to simplify as far as you possibly can. Okay? That's for identities. In the program for this topic, this year, the thing they focus on using this for is not for proving identities, but for solving equations. Okay? So let's do an example, and I'll show you how this is just an alternative method for solving it. We'll do one, which you can do by auxiliary angle as well. Okay? So we'll do it this way, and then we'll do auxiliary angle. Okay. So I think when I was introducing or reintroducing auxiliary angle, this is the example we were going with, so let's just go with it again since it's familiar. This is just an expression, but to make an equation that we want to solve, let's let it equal to, say, 1. Okay. So how would we solve this? Like I said, and we will do this in a minute, you can convert this left-hand side into an r sine x plus alpha. Right? We will do that and you'll get the same solutions, fingers crossed. Okay. How would we do it here with the t result? Well, you're simply going to bring these guys in. Okay. You do have to say let, okay, because we're about to bring in t. Where'd t come from? And sometimes t will be equal to different things. Remember, sometimes you don't use x on 2, sometimes you'll use 2x or 3x or whatever suits your question, right? So let's let tan of x on 2 equal to t. And now I can actually substitute all of these results that I'm familiar with. Okay? So 2t, 1 plus t squared, and there's cos. Okay, so what do you think is the best step to go with to start simplifying this? I can consider these two as 2t plus 1 minus t squared, right? And I've got this on the denominator, which is the same, okay? So if I'm going to do both those at the same time by multiplying across, because it's the same denominator, right? And I don't like fractions. So there you go, multiply across. We've got t squared here. Actually, I might bring them over to the right hand side and try and keep things positive. My ones, they're gonna cancel, so they disappear. Okay. And then over on the right hand side, I add t squared to both sides and subtract 2t. Okay. You can take out your factor of 2, and then you can factorize this as well, so you'll actually end up with this. Okay, so far so good. So from here, I remember what t is. It's tan of x on 2. Oh, sorry, I forgot something. I'm a bit naughty. This is not a general solution, so let's supply a domain. What would I expect? 0 to 2 pi. Now, the reason why I remember that this is important now is because this function we've introduced that we're solving with respect to t is equal to 0 or 1. So tan of x on 2 is equal to 0 or 1. Domain's important, right? It's important because it limits the number of solutions you've got, but also because this function is not in terms of x, it's in terms of x on 2, right? That also affects the domain you're solving with respect to. So up here, I'm going to convert this domain into the one that my function is speaking in terms of. Okay? So if I want this to be an x on 2 instead of an x, I've divided that by 2, so I'll divide everything by 2. So the 0 remains unchanged, and the 2 pi turns into a pi. Okay. So now, when I think about the solutions to these, tan of x on 2 is equal to 0, and tan of x on 2 is equal to 1. As you're thinking, okay, what values will give me 0, and what values will give me 1? This is the domain that you're restricting yourself within, okay? Not this one, because it'll give you extra solutions. Okay, 0. What's tan look like, and where does it hit 0 in this domain? The first one is 0, because it starts there, right? So x on 2 equals 0. There's 1. And then you've got an asymptote, and then it comes back up like that. So there's 0 to pi, so I've got another solution right there. Okay, so 0 or pi, that's x on 2, so we just multiply through and get our two solutions from this side of the equation. Happy so far? Tan of x on 2 is equal to 1. Again, you come back to your domain and your graph. Within this domain, there's just the one solution, and this is an exact value. What value is it? Pi on 4, good. So x on 2 is pi on 4, so you multiply, and there's another solution. Okay, so 1, 2, 3, so let's just tie it up and say x equals 0, pi on 2, or 2 pi. Happy.